Today's seminar is using reduced numerical precision on Pascal, Volta and Turing GPUs. So first, a bit of motivation. Why lower precision? Well, it turns out that in deep learning algorithms, which have become extremely popular in recent years, you can get satisfactory results with lower precision. This has something to do with the fact that deep learning algorithms are analogous to how biological brains work, and it's sort of intuitively obvious that your brain, which is a kind of a messy, bubbly biological entity, probably doesn't store the potentials between neurons to 16 decimal places, and it still seems to work. So it seems to be error resistant in a certain way, and that's how deep learning algorithms are as well. So you can solve your deep learning problem in lower precision, and that's good because lower precision means you need to use less memory and you can do more computations. And in fact, you can take this precision to the end of the spectrum, so to speak, and you can have lower and lower precision for various tasks. In particular, training the neural network might require some kind of precision, but then using it might be acceptable with an even lower precision. But I hope that this talk, by showing you how to use these features on GPUs, these lower precision features, you can also maybe get some ideas about using these tools in other fields outside of deep learning. So to give you now the timeline of what NVIDIA has done to support reduced precision. So first, the Pascal GPUs support FP16 type. So this is half precision floating point with 16 bits, and that can run on just conventional floating point FP32 CUDA cores. Then we have next generation Volta GPUs added a specialized computational unit called the Tensor core on the Volta, which significantly increases the amount of computation you can do on high precision numbers. And finally, the latest generation has the Tensor cores, but those, in addition to half precision floating point operations, they also support integer 8, integer 4, and BOOL matrix multiplications. So let's talk about what does lower precision mean exactly. So the usual floating point number that we are all used to in our programming is a 32-bit float. So this uses 32 bits to actually represent a floating point number. So in all these representations, we have a challenge that we have the real line, which is continuous and has infinitely many numbers. And somehow, if you want to use those real numbers somehow on a computer, we have to represent them with a finite number of bits. So if we are using 32-bit floating point storage, then the convention is we have 1 bit for to store the sign, 8 bit to store the exponent, and 23 bit to store the fraction. So this is a conventional storage, and 2 to the power of 32, which is the total number of bit permutations we can have, zeros and ones, so to speak, is about 1 billion. So we can represent 1 billion numbers. And we know that if for some computational tasks we need even more precision, we can have double precision, where we store a number with 64 bits, and that gives us 10 to the 19 possible combinations of 0 and 1s. But what about if you want to reduce the number of bits? So if you want to use 16 bits, so we can do that, and that's half precision. So in this case, we have 1 bit for the sign, 5 bit for the exponent, and 10 bit for the fraction, the significand, so to speak. But the total number of possibility is 2 to the power of 16, and that is only 65,536. So this is a disturbingly low number, right? Because we are going to have to try to represent all of real numbers, which are infinite and continuous, with at most 65,000 numbers. So for certain problems, this will work fine, and for other problems, it will not. And I will show you in the next slide exactly what this kind of storage implies. But what if you want even lower precision? Well, it really doesn't make much sense to try to store a floating point number using 8 bits or 4 bits. It's just, you run out of bits. So for lower precision, you use integers. So in particular, there is 8-bit integer, So for 8-bit integer, you have 2 to the 8 equals to 256 possibilities. And you're familiar with this data type as just char in C programming. Char is a 8-bit integer. To go even lower, there's int4, only 4 bits, which means only 16 possible values. And finally, the lowest possible bool, which is just Boolean true false. So there's only 2 possible values, 0 and 1 for that one. Okay, so let's look at a little bit more detail at half precision. So here's how half precision 16-bit integer stores its data. So we have 1 bit for the sign, 5 bits for the exponent, and 10 bits for the fraction. So it seems like we have 32 possible values for the exponent. But actually, we separate these into 30 what are called normal values and 2 special values. So the 30 normal values from 1 to 30 are what are called, they represent so-called normalized normal values. And the expression for the actual floating point value is here. So we take -1 to the exponent sign bit. Whatever your sign bit is, this determines the sign. And then we take our exponent number and we subtract 15 from it. And this gives us the actual exponent we apply to 2. And then we multiply this by 1 times whatever is in our significant bits. And notice that everything here is in base 2. So we have a decimal number, but actually in base 2. One nice thing about such numbers is that each non-zero binary number which is greater than 1 always starts with 1. So we don't have to store the 1 because we can just assume to be there and we can store the rest. So this is how we represent so-called normalized value. But then there's a special way to represent the numbers close to 0. So if our exponent bits are all 0, this means that we have what is called a subnormal number. And in this case, if these bits, if the significant are 0, then we just have 0 or -0. Actually, you have both. But if this is non-zero, then now the leading digit might be 0. So these are, in a sense, numbers smaller than the smallest number which can be represented with the normalized value. And finally, there's a special code reserved for infinities and not numbers. So, if you add 2 floating point numbers and they exceed the maximum possible value, then the result is set to either infinity or plus infinity or minus infinity. And if you try to divide by 0, then the result is set to the other number. Okay, so with this representation, what does this mean in practice? Well, I will just show you 3 examples of what kind of half-precision floating numbers we get. So if our bits are this, 0, 0, 0, all zeros, and except 1 at the end, that means we have 2 to the power -14. And because these are all zeros, this is a subnormal number. So this evaluates to 0 plus 1 over 1024, which is this number. So this is the smallest possible positive floating point number which we can represent with half precision. Then let's look at the next interesting number, smallest possible normal. So here we have 0, exponent is 1, so the lowest possible exponent as well. But now the number is 1 plus 0 over 1024, which is this. So this is the smallest positive normal number. And finally, let's look at the other end. What is the highest number we can represent? So here we have our exponent, which evaluates to 2 to the power 15. And the significant is all 1, so this is 1023. And then the resulting number is 65,504. So these are the 2 extremes. So in half precision, this is the smallest number we can represent, and this is the largest number we can represent. So you can notice that for some problems, this is perfectly fine, but for some other problems, you might frequently get a number above 65,000, for example. So if you have that kind of a set of data, then you cannot use half precision to represent it. So you have to worry about the limits, but you also have to worry about the spacing between numbers. For example, note that the spacing between numbers is increasing as the exponent is increasing. So for the largest numbers, so for the numbers represented by exponent 2 to the 15, so these are the 1024 numbers below 65,504, the spacing is 32. So the spacing between numbers you're representing is 32, which is actually relatively large. So if you want to use, in a general problem, if you want to use half precision, you have to look at these limits and see whether your data can tolerate these limits. Okay, but let's assume that you have data which can tolerate these limits. So in that case, you have many incentives to actually use half precision. Because if you use half precision, well, you can store twice as much data, right? You can store twice as many data items because each one of them takes only half the amount. And as we all know, the GPU memory is relatively limited. So if you have a data set which is hard to fit into memory of your GPU, well, then making it half the size would be quite beneficial. And there's also benefits to computational speed because it turns out that a single floating point core, CUDA core, can actually do two half precision operations in one cycle versus one normal precision operation in one cycle. So you can potentially get a factor of 2 speed up as well. And finally, you can use the tensor cores on these half precision numbers, which I will mention later. So let's look at the simplest case. So here I take a problem which I use in our summer school frequently, which is Saxby, just adding, taking a vector, multiplying it by a constant, adding another vector, and storing this in a new vector. And I took my code for this, and I converted it to half precision. So I will show you my code, and I highlighted in bold the changes I have made. So first, I need a type to store half precision numbers. And this type is called half. And this is provided by CUDA. So you have to have a include file, CUDA_FP16, to have this type defined. Okay, so once I defined it, I make all my vectors type half. So I have half vector y, half vector x, half alpha. And in this example code, I have a kernel which computes this addition, and I also have a CPU function which computes this addition as well, so I can compare the results. But note here that the half data type is actually a device data type. It is only also all the operations on it, like adding 2 of this data type, is only defined on the GPU. So if I try to add 2 elements of this array on the host, on the CPU, I will get an error. So to make this possible, I have to use a special function which converts from half precision to float. And once I do this, then I can use this on the host. So here are my kernels, and here's my main code. So I define pointers to my arrays with half data type, and then I allocate memory with half type. So memory size is size of half, and the pointer cast is half. But other than this, my code doesn't change. And then when I fill out my half arrays, half data type array, I just use a floating point number, which gets automatically, when I assign it to a half data type array, it gets converted to half without any special steps. So that's convenient. And other than this, the code is unchanged. So CUDA memcopy works as before once I have defined my mem size properly. And I download the results. And so I do the addition, I download the results, and then I want to check the results. And here again, I have to use the half to float conversion, because in the host code, I cannot use the data type directly to perform operations on it. So this is my Saxby code. And now let me time it just to show what the benefits of using half precision are. So first, I have some results on the P100 GPU. So this is Pascal. And the numbers I got are from NVProf, so the NVIDIA profiling tool. So basically, you can tell here that this is the float result. So this is using 32-bit precision. And this is the half result. This is the 16-bit precision. And basically, everything shrinks by a factor of 2. So my mem copies, so notice here, device to host, 195 milliseconds. This goes down to 97 milliseconds, about half. Because my data is now 16-bit, not 32-bit, so things move twice as fast. And the computation shrinks by about, the computation time for the kernel shrinks by about a factor of 2 as well. So this is due to both the fact that when I'm getting data from the global memory to the CUDA cores, I'm only having to get half the data, so it should be going twice as fast. But also the CUDA core can do 2 half precision operations in the time it takes for it to do 1 normal precision operation. And the results on the V100 are basically exactly analogous. So the transfers for the float, once I switch to half precision, everything shrinks by half. Everything becomes twice as fast. The transfers take half the time, and the computation takes about half the time. So the message here is that as long as you have data which can tolerate being represented in half precision, there's basically no reason not to switch to half precision when you're using the GPU. Okay, so the half precision was implemented already in Pascal generation cards, but in Volta generation, NVIDIA went beyond this and they introduced what are called tensor cores. So tensor cores are special computational units which specialize in performing exactly the operation shown in this slide. So it's matrix multiplication and addition. So a tensor core can, in one cycle, take a 4x4 matrix and multiply it by another 4x4 matrix, where the inputs are in half precision, or FP16. And then it can take the result and add it to an accumulator, which is either half precision or full precision. So this means that if you're doing this operation in a single cycle, you're doing 64 multiply add operations, and a multiply add operation is a multiply and an add. So if you're counting operations in floating point numbers, you have 128 operations in total in a single cycle. So this is a mix of half precision and full precision, depending on how you do it. So this is the basic operation available on Volta cards. And then the next generation, the Turing cards, also have tensor cores, but these now support analogous operation on 8-bit integers, 4-bit integers, and BOOL numbers, where the accumulator is integer 32, so a normal precision integer. So to illustrate this better, let's take a look at the circuit layout of a Volta multiprocessor. So you can see here that we have 32 floating point 64-bit cores, so 8, 8, 8, 8, and we have 64 floating point 32 cores, so 16, 16, 16, 16 in total. And we also have 8 tensor cores inside the multiprocessors, 1, 2, 3, 4, 5, 6, 7, 8, 8 in total. So your floating point 32-bit cores, there are 64 of them, and each one of them can do a half precision floating point per cycle. So it can do 128 FP16 ops per cycle. But there's 8 tensor cores, and each one can do 128 mixed precision 16 and 32-bit floating point operations per cycle. So you can see from this then that the total computational power of a single multiprocessor, when you're talking to these kind of matrix multiplication operations of this specific type, you get 8 times the performance out of the tensor cores compared to the performance you would get out of just standard floating point cores. So for the whole GPU, this means that when you have 80 streaming multiprocessors in a V100 GPU, your performance for just normal precision floating point is 15.7 teraflops, but your performance for this special type of matrix operation multiplication using mixed half precision and full normal precision is 125 teraflops. And this is just a factor of 8, so 8 times this is 125. So you can see that you can get potentially an 8-fold boost in performance out of a single multiprocessor and out of the card as a whole if you're doing this type of operation. Now, we have to keep in mind that some calculations are memory bound. So, seeing this kind of 8-fold increase in performance assumes that you can get your data to the streaming multiprocessors from global memory fast enough. Let me also show you a circuit diagram for the next generation. This is the Turing card. So This also has 64 CUDA 32-bit floating point cores. So that has 128 floating point 16 ops per cycle, as Volta did. We have 8 tensor cores, so we have 1024, 8 times 128 equals 1024 mixed precision ops per cycle. But in addition, Turing now supports integer operations as well. So if you use integer 8 as input and integer 32, so normal integer, as accumulator, you can do about 2,000 operations. If you use int4 and int32 as accumulator, you can do 4,096. And finally, if you use bool and int32 accumulator, you can use 16,000. So you can see that as long as you have a problem for which data can be represented with such extremely low precision, you can get huge performance gains in terms of the number of operations you can do per cycle. And it just so happens that deep learning problems, especially the inference part of them, so when you have trained your network and you want it to answer some question for you, that's where the integer operations are useful. So the total performance of this card, we have, it's about, so we have half the number of streaming multiprocessors compared to the V100, so there's 40. And this means we have 8.1 teraflops single precision floating point, 65 teraflops half precision. So, and if we are talking about int4 operations, we have 260, so 4 times. So notice that here for int4 we go from 1024 to 4096, so that's a power of 4 increase. So we go from 65 to 260. But it's useful to keep in mind that the Turing card is a low power card. It uses much less power than the V100. So it is quite likely that you're going to have some throttling effects if you try to run this card. So sometimes the clock will be decreased when the card is using up too much power. And the final note here is that this card has no FP64 cores at all, no double precision cores, as you can see from this diagram. So it's not really useful for typical physics engineering simulations, which require double precision. Okay, so finally, let me now show you how would I actually use these tensor cores in CUDA code. So many of you might simply end up using some library which already has this implemented for you. Let's say if you're using TensorFlow, it will just be implemented inside the program. But here I will show you what would you have to do to actually use those features inside your code. So to access tensor cores, you use what is called a warp level matrix operations template library, WMMA. Now the interesting thing about the functions of this library is they are called per warp. So you have to think of these operations as executed by a particular warp. Also, you cannot, this 4x4 matrix multiplication that I've shown you before, you cannot actually access it directly in CUDA code. Instead, you have to do the operation when the matrix sizes have the following 3 exact combinations. So you can have 16 by 16 matrix multiplied by another 16 by 16 matrix and then add 16 by 16. So the shorthand for that, to just get this in a compact notation, is 16 by 16 by 16. And the other 2 allowed possibilities have 32 by 8 matrix as result with 32 by 16 as input, and an 8 by 32 matrix with 8 by 16 and 16 by 32 as input. So 16, 16, 16, 32, 16, 8, 8, 32, 16. These are for now the only possibilities. And the possible data types, so on Volta and later cards, the input matrices can be half precision, floating point 16, and the accumulator matrices either half precision or full precision. And then Kepler cards add the possibility to have input matrices as int8 and accumulator matrices int32. And finally, there's experimental support for int4 and BOOL. And notice that for these, the allowed matrix sizes are a little bit different. Only one matrix size is possible. Okay, so how would we actually do this in code? Well, to illustrate, I will show you a very simple code which just multiplies 2 16 by 16 matrices together. This code will be using a single block of threads with 32 threads in it. So we have exactly 32 threads in the block. That means we have exactly 1 warp. So what we will do is we will take each matrix, each square, and we will map it to an object called WMMA fragment. So this is a special data structure which, once we put data in there, we can make it available to the Tensor Core, and then we can do other WMMA operations to actually perform the multiplication. So specifically, I will show you the code in the next slide, but let me just talk you through what the code will do. It will initialize the data on host. It will copy to the GPU. Then inside the kernel will initialize the fragment. It will fill the result fragment with 0 because one of the inputs is the accumulator, so we have to set this to 0. And then it will copy data from the global memory to the fragment with load matrix operation. Then it will do the multiplication, the matrix multiplication with MMA sync call. And finally, once it is done, it will copy the result back to global memory. So here is the kernel code which does this. So this is the kernel part of it. So you can see that I have three matrices, A, B, and C. So I call the fragment operation. And here so my input data is A, and everything is 16. So the fragments are 16 by 16. So I define them. Then I fill the fragment C with 0. So this is fill fragment. And here I load the inputs. So I load from the global matrix A into the A fragment, and I load from the global matrix B into the B fragment. So, and this is the last number here is the leading dimension of my array, which is 16. So once I have loaded the numbers, I perform the matrix multiplication with MMA sync. And once that is done, my result is stored in this C fragment. This is the result fragment. And now I have to do a store matrix sync operation, which takes the result out of the fragment and puts it into the global matrix again. So really what we are doing here is, if you want to use Tensor cores, you have to have this intermediate step where whatever data you are working with, you are copying it from your global array into a fragment. And all of these fragments are defined per warp. So threads belonging to the same warp will see the same fragment. So this is something quite interesting because in other CUDA code, warps are not so directly present. They are sort of implicitly present, but you don't actually see them. But here we are explicitly seeing code which is executed per warp. But note that in this example, we have only one warp, so everything is very simple. And just to show you, this is the host part of the code. So I notice that this is a mixed precision operation. So my C matrix is stored in floating point precision, so FP32. This is why we have float here. And the inputs are stored at half precision. So this is why we have half. So I define my arrays, 16 by 16. A, B are half, and C is float. I do a CUDA malloc, and the size half and float is appropriate. I initialize the half precision input matrices. I copy the data, and I call my kernel. So nothing special here. This is similar to what we have seen for the Saxby example. Now things get more complicated when I have a larger matrix and I have more warps, because this now means that I have to take my matrix and I have to divide it into chunks, and each chunk will go to a particular warp for the computation. So in the next example, I will have a 32 by 32 matrix. So I need to break it up into 4 16 by 16 blocks. And so each 16 by 16 square below is going to be mapped to one WMMA fragment processed by one warp. So, by the way, the example I'm showing you here is quite inefficient. This is just for illustrative purposes only. If you want to see an example which actually is more serious and tries to optimize using various techniques, then you can find one in CUDA samples, CUDA 10 samples, under samples, simple CUDA Tensor Core Gem. So, so let's take a look at the code. So now I have 4 warps. So in particular, each warp is identified by having a different combination of block idx.x and block idx.y. So to help myself, I can define 2 variables called mwarp and nwarp. And now I define my fragments, but the interesting thing that will happen now is that the data I am copying will have to come from different different parts of the matrix. So in particular, depending of what my warp number is, Each warp will then load the data from a different address, and it will do the multiplication, and then it will store the data at a different address. So now you have this additional complication that each warp has to know where to get the data from and where to put it. And the main code is quite similar to the code before, except now my matrix is larger. Okay, so hopefully this shows you how to use the Tensor cores. It is a little bit awkward, and they are definitely highly restrictive. I mean, all the Tensor cores can do is those simple matrix multiplications on those very small matrices. So in real life, you probably wouldn't really want to jump into programming with Tensor cores, but let me show you how you can use them by using a library. So let's see, how could you use Tensor cores to accelerate your linear algebra operations? So to do this, you have a bunch of possible libraries out there. I will talk about cuBLAS, which is the standard CUDA version of the BLAST library, which comes with CUDA, so it's always available. Now, to use Tensor cores, only one cuBLAS operations supports Tensor core use, as you would expect, and this is the general matrix multiplication, or GEM. In particular, SGEM, which is the standard floating point multiplication, supports Tensor cores. But what this means in practice is that it takes your input matrix of 32-bit floating point, and it converts it to 16-bit floating point, so it downgrades it. So when you use Tensor cores on this operation, you actually lose some precision, so you have to keep this in mind. But you do get an increase in speed. Then there is the half-precision matrix multiplication operation, HGEM, and you can accelerate this on the Tensor cores. And finally, it is also possible to do mixed precision. So you can have input with floating point 16 and output with floating point 32. And also you can have various other mixes of types, including integer 8. And finally, the final thing I should say is that when you're using cuBLAS with Tensor cores, if you actually want to use Tensor cores, you have to explicitly enable them. If you don't enable them, they are not being used. And this has to do with the fact that the use of Tensor cores possibly leads to loss of precision. So cuBLAS tries to ensure that you actually consciously want to use Tensor cores. So finally, let me show you the numbers from some benchmarking I did on matrix multiplication using cuBLAS. So first line is the V100 result for the normal single precision 32-bit floating point. Without Tensor cores, I get 12.8 teraflops. With Tensor cores, I get 36. So I get about 2.8-fold speed up. Though keep in mind that this is with some precision loss, because I'm converting the results to 16-bit floating point. So there's definitely some precision loss there. Here is the all half precision, so both the input and output are half precision. So without Tensor cores, I get 27 teraflops, and this goes up to 94 teraflops. So a factor of increase by about a factor of 3.4. And then let's look at analogous results on the T4 card. So a T4 card has half the multiprocessors and potentially runs at lower power, so it throttles more than the V100. So this gives me 4.3 teraflops without Tensor cores with single precision, and this goes up to 7.5 with Tensor cores, so it goes up to about 1.7. And then for half precision, I get 9.1 teraflops, and this goes up to 20 with Tensor cores, so by about a factor of 2.2. So notice that the speed up is not a factor of 8, so the theoretical maximum could be up to 8. But I think what is happening in this case is we have a memory bound problem. So it's just the data transfer from the global memory to the streaming multiprocessor saturates. So we just can't get the data to the Tensor cores fast enough. But nevertheless, you can see here that if you either have code which uses half precision data types, or you have code which uses single precision, 32-bit, but which can tolerate a conversion to half precision when you're doing matrix multiplication, then you can get about a factor 2 to 3.5 speed up by enabling Tensor cores on these GPUs, which is, it's pretty nice possibility to have basically for very little modification to your code. So I hope that this seminar has introduced you to the idea of lower precision features available on the GPUs and how you can potentially use them. Thank you.